26.209 Grounding and Bonding. Section 2.0.0 Service Grounding Methods. Identify and describe service grounding methods. Explain how to size and install a grounding electrode conductor. Explain how to select other electrodes. All electrical systems must be grounded and bonded in a manner prescribed by the National Electrical Code to protect personnel and equipment. A grounded system must limit the voltage on the electrical system and protect it from these three primary threats: lightning, voltage surges higher than that for which the circuit is designed, or an increase in the maximum potential to ground due to abnormal voltage or contact with a higher voltage line. Requirements for grounding of services are found in NEC section 250.24. Methods of grounding an electric service are covered in NEC article 250 part 3. In general, all of the following electrodes that are present must be bonded together to form the grounding electrode system. So if any of these are present, they all have to be bonded together. An underground metal water pipe in direct contact with the earth for not less than 10 feet. Metal in-ground support structure as described in section 250.52A2 of a building or a home. An electrode that is encased by at least 2 inches of concrete located within and near the bottom of a concrete foundation, or footing that is in direct contact with the earth and consists of at least 20 feet of one of the following: electrically conductive coated steel reinforcing bars or rods at least ½ inch in diameter, or bare copper conductors of number 4 gauge or larger. A ground ring encircling the building or structure in direct contact with the earth consisting of at least 20 feet of bare copper number 2 gauge or larger. A rod, pipe, or plate electrode. Other local metal underground systems or structures. So if any of those are present, they all have to be bonded together and used. Underground metal water pipe cannot be the sole means of grounding. If you have a metal water pipe, it has to be grounded. It has to be bonded to the grounding system, and a supplemental ground rod has to be driven into the ground, into the earth. You cannot use the water pipe as the sole means of grounding. So any metal in-ground support structure, an electrode that is encased by at least 2 inches of concrete, I think they call that an OOFR ground, a ground ring, rod pipe or plate electrodes. If you have a gas pipe, metal gas pipe, it cannot be used as a grounding electrode, but it does have to be bonded with a number 6 wire to the grounding system. Grounding electrode systems used in industrial buildings will frequently use all of the methods shown in Figure 10, and the methods used will often surpass NEC coverage depending upon the manufacturing process and the calculated requirements established by plant engineers. So here's a panel. Here is the grounding electrode conductor, and it's going to either a ground ring or a ground plate. That's a minimum of 2 square feet. So that's 1 square foot, but it has 2 sides, and both of those sides are in contact with the earth, or a rod or pipe or iron or steel, a water pipe, and it cannot be the sole means of grounding. You have to supplement it with a ground rod, or the building steel. All of these, if they're present, they have to all be bonded together. Here it says grounding system floor plan for an industrial building. They have cold water pipe. It has to be bonded. They have a ground ring encircling the building. They have the building steel, the rod iron in the concrete, electrode encased in at least 2 inches of concrete at the bottom of the footing, consisting of at least 20 feet of one or more ½ inch steel bars, or bare copper at least number 2 gauge or larger. Every I-beam will be bonded, CAD welded to this ground ring going around the building. If more than one method exists in one building, they must all be bonded together. Here's a highlight. It says the building also has a metal underground gas piping system, but this may not be used as a grounding electrode per NEC section 250.52B1. However, the gas line must be bonded to the electrical system if it's likely to become energized per NEC section 250.104B. And Figure 12, grounding requirements for non-industrial buildings. Again, familiarize yourself with the panel. Here's the main bonding jumper, the neutral bus, and here's the grounding electrode conductor coming outside. Here's the grounding clamp, the connection made within 5 feet of the point where the pipe enters the building. This is a water pipe. This is building steel. This is the ground rod, grounding clamp. Upper end of the rod must be below the permanent moisture level, if practical, and it has to be in contact with the earth for at least 8 feet. So if it's 10-foot rod, if 8 feet of it is below the moisture level, you're good. Grounding electrodes need to be spaced at least 6 feet apart. So where you have a cold water ground, if you're going to supplement it with a ground rod, that ground rod has to be at least 6 feet away from that cold water ground. Metal underground gas piping system may not be used as a grounding electrode. Here's a highlight. NEC section 250.53D2 further states that the underground water pipe must be supplemented by an additional electrode of a type specified in NEC section 250.52A2 through A8. It can't be the sole means of grounding. Since a metal in-ground support structure, concrete and clay-cased electrode or ground ring is not available in this application, NEC section 250.50 must be used to select the supplemental electrode. In most cases, this supplemental electrode will consist of either a driven rod or pipe electrode, the specifications for which are as follows. If it's stainless steel or non-ferrous rod, it has to be a minimum of 1/2 inch diameter. If it's iron or steel, it has to be a minimum of 5/8 inch in diameter. And if it's a pipe or conduit, it has to be a minimum of 3/4 inch in diameter. And minimum 8 feet of that ground rod has to be in contact with the earth. You may not use aluminum. Aluminum cannot be used as the grounding electrode or as the grounding electrode conductor. They must be able to withstand and dissipate repeated surge circuits. They must be corrosion resistant in various soil chemistries to ensure continuous performance to protect the life of the equipment. They must have rugged mechanical properties for easy driving with minimum effort and rod damage. Plate electrodes offer an alternative to the pipe or rod method. Each plate electrode must be exposed at least 2 square feet of surface to the surrounding earth. Plates made of iron or steel must be at least 1/4 inch thick, while plates of non-ferrous metal like copper only need to be 0.06 inches thick. So they're very thin, but you are exposing 2 square feet when the plate is 1 square foot and it has 2 sides in contact with the earth. Single rod, pipe, and plate electrodes must have a resistance to ground of 25 ohms or less, as shown in Figure 13. If not, they must be supplemented by an additional electrode spaced at least 6 feet away from the first. So you can take an ohmic reading of that ground rod or that grounding electrode, and if it's greater than 25 ohms to ground, you have to supplement it with a second ground rod. Grounding electrode conductor is the sole means of connection between the grounding electrode and the grounded system conductor. In an ungrounded system, it may be the sole connection between the grounding electrode and the service equipment enclosure. So a common grounding electrode conductor is required to ground both the circuit grounded conductor, that's the neutral, and the equipment grounding conductors. Figure 14 shows the common connection for this system. So here's the grounded conductor coming in the neutral. Here are equipment grounding conductors going out on branch circuits. And here's the grounding electrode conductor going outside to the grounding electrodes. Here's a main bonding jumper tying all of them together and to the case of the panel, the main panel. Sizing the grounding electrode conductor, again, table 250-66 in the code book. The size of the service entrance conductors is determined from the ampacity of that system. NEC table 310-16 is used to determine the size of the service conductors for its ampacity. So let's take a look at that. Here's Article 250. Let's look at 250-66. That's going to tell us about the grounding electrode. Let's see here. Maybe I better speed ahead here. I thought I could just scroll through these pages here. Hold on. I'm afraid of going too fast if I scroll. Here's Table 25066 grounding electrode conductor for alternating current systems. And it goes by the size of the ungrounded conductors. So 2 watt to 3 aught copper ungrounded conductors, the surface entrance conductors, you'll need a minimum of a number 4 copper or a number 2 aluminum grounding electrode conductor. And again, you don't want to use copper clad aluminum or aluminum because you have to stop within 18 inches of the ground and switch over to copper anyway. You cannot go to the grounding electrode if it's within 18 inches of the ground. So you might as well just go ahead and use copper to begin with. This is that 25066 table, and it shows you the size of the copper ungrounded conductors or the aluminum ungrounded conductors, what size of copper or aluminum grounding electrode conductor you need to use. Again, don't use aluminum. You can only use it to within 18 inches of the earth. And then the load side grounding is 250-122. 250-102 actually shows us the size of the main bonding jumper. The grounded conductor, the main bonding jumper, the system bonding jumper, and the supply side bonding jumper for alternating current systems. So again, it goes off the size of the ungrounded conductor, and it tells us the size of the main bonding jumper, the grounded conductor, which is the neutral conductor, or the supply side bonding jumper for alternating current. 250-122 is the equipment grounding conductors, and it goes off of the size of the overcurrent protection device, not the size of the ungrounded conductors. So here's table 250-122, minimum size equipment grounding conductor for grounding raceway and equipment. And again, it goes off of the circuit breaker. So a 20 amp circuit breaker is a minimum of a number 12 copper equipment grounding conductor. Up to 60 amps, you can use a number 10 equipment grounding conductor. Up to 100 amps, you can use a number 8 equipment grounding conductor. Up to 200 amps, you can use a number 6, and so on and so forth. If for any reason you ever got larger than 6,000 amps, which is crazy, the equipment grounding conductor has to be a minimum of 12.5% of the cross-sectional area of the ungrounded conductor. All right, let's go back to the book. Very good. So that was the table 250-66, and we also looked at 250-122. Here's a highlight. Once the size of the service conductors is known, the size of the grounding electrode conductor can be determined from NEC table 250-66. Again, that's called the line side grounding. Determine the size of the service conductors from NEC table 310-16. Go down the left-hand column of table 250-66 and find the size of the ungrounded conductor. Go across to find the size of the grounding electrode conductor for a copper electrode. The required size is a number 4. Installing the grounding electrode conductor. The grounding electrode conductor must be copper, aluminum, or copper-clad aluminum. The material selected must be resistant to corrosive conditions in the area, or it must be suitably protected against corrosion. The conductor may either be solid or stranded, covered or bare, but it must be in one continuous length without a splice or joint, except for the following conditions. Splices and bus bar are permitted. Where a service consists of more than one single enclosure, it's permissible to connect taps to the grounding electrode conductor. Bonding jumpers from grounding electrodes and grounding electrode conductors can be connected to an aluminum or copper bus bar not less than a 1/4 inch by 2 inch. See section 250.64F3. Warning: exothermic welding is a hazardous process that should be performed only by qualified personnel. Refer to your company's safety procedures and the manufacturer's recommendations before using exothermic welding. Exothermic welding is joining the grounding electrodes and the grounding electrode conductor together metallurgically. Basically, you have some slow burn gunpowder along with copper filings and other pieces of metal, tin, and what have you, in a powder form. but it's a slow burn gunpowder. You can strike it with a flint or a striker, and once it starts to burn, it'll continue to burn, and it'll melt the copper and the tin, and it'll run down in this mold, and it forms this exothermic weld between the ground rod and the grounding electrode conductor. Or you can do it with building steel. I've used them before where you uh, metallurgically connect the grounding electrode conductor to the side of an I-beam with this exothermic welding. All right. If you wanted to bury your ground rod at your house, you have to exothermically weld the grounding electrode conductor to the grounding electrode and then get it inspected by the electrical inspector. When they approve it, then you can bury a ground rod. You don't have to have that ground rod protruding out of the ground where you might hit it with a lawnmower or weed eater or what have you. You can bury it, but it has to be exothermically welded. You can't use a mechanical lug or an acorn clamp on a ground rod and then bury it. All right. Let's see here. NEC section 250.64b requires the grounding electrode conductor or its enclosure to be securely fastened to the surface on which it is carried. Number 6 gauge and larger conductors require protection where physical damage is possible. If free from exposure to physical damage, number 6 gauge and larger conductors may be routed along the surface of a building and be securely fastened. Otherwise, the conductor must be protected by installation in rigid or intermediate metal conduit, rigid or non-metallic conduit, EMT, or cable armor. Smaller conductors must be protected in conduit or armor. See section 250.64e. So here are grounding electrode conductors, and they're all going to a main grounding bus, and they're all going down to these conduits. They also have these, they're bonding bushings or meg bushings on the top of these conduits, and they have a clamp on each one of them, and then this conductor goes through them, and it is bonded to each one of these, so that all the pipes are bonded as well. Other electrodes. When an electrode that meets the requirements of NEC section 250.50 is not present, other electrodes may be used. These may be the rod and pipe electrodes discussed earlier, other listed electrodes, plate electrodes, or other local metal underground systems such as piping and underground tanks. NEC section 250.52A4 through A8 provide information about these electrodes, while NEC section 250.53 provides their installation requirements. The specific requirements for other electrodes are as follows. Local systems, local metallic underground systems such as piping, tanks, metal well casings, etc. Rod and pipe electrodes. Pipe or conduit electrodes must not be less than 8 feet in length, nor smaller than 3/4 inch pipe size. Plate electrodes must have at least 2 square feet of surface area in contact with exterior soil. If it's made from iron or steel, the plate shall be at least 1/4 inch thick. If it's made from non-ferrous metal like copper, it will be at least 0.06 inches thick, which is 1.5 millimeters. Here's a highlight. Underground metal gas piping systems and structural reinforcing steel members described in NEC section 680.26b1 and b2 are not permitted to be used as grounding electrodes. However, this does not eliminate the requirement that these systems be bonded. So, exothermic welding. It's the connection made by exothermic welding are considered permanent. They perform better than any crimped or bolted connection because the copper to copper or copper to steel bond is molecular, eliminating the risk of corrosion or loosening of the joint. Exothermic welded connections can carry more current than the conductor, resist repeated fault currents, and will not deteriorate with age. Section 2 review. Assuming the use of 75-degree copper conductors, a 200 amp commercial service would require what size service entrance conductors? And a ground rod must be installed in a coastal location and can only be driven halfway before encountering a rock shelf. One legitimate alternative is to, I don't remember that we went over that, but you can bury the rod in a trench at least 30 inches deep. It tells you that the rod has to be vertical unless you encounter a rock, and then you can put it at an angle not greater than 45 degrees. And if that doesn't work, you can lay it in a trench 30 inches deep and just bury it. So it's kind of funny that they start off telling you that it has to be vertical, and they end up telling you you can lay it in a trench. All right, I'll stop here and go on with another video.